Hello, calculus student. This video is for chapter 2.3, the limit laws. The limit laws is used to evaluate limits analytically or algebraically, so we have an exact answer. In 2.2, we talks about we can find limit by listing tables of f of x, except when x approaches a. We're talking about finding limit x approaches a of a function, right? So, and we said that, well, we just, the concept of finding a limit is not to investigate when x is equal to a, but what happened when x is close to a, what is the f of x approaches. So we find that, well, then just do tables or look at graph, but they are time consuming, take up a lot of resources, and you may not have exact value. That's actually the big problem. So we need another method that can calculate limit accurately without going for graph or tables. So the basis of doing this is something called the limit laws. So I did not copy the limit laws over here. So I'm just going to show you the book version of it. The limit laws say that if I have two limits and they exist for f and g, if I add f and g, then the limit is f. Just the two limits add together. If I subtract them, is the two limits subtract. If I multiply one of them by a constant, then it would just be multiplied by the limit. So it seems reasonable. This looks very well. But where do we have these two limits to start with? It turns out that we do have two limits. That is very important. That we mentioned at the back of at the end of 2.2, which is the two limit of the identity limit here. Okay, so the identity limit means limit x approaches a, the function is x. So of course the function is going to approach a, so the limit is a. And the limit x approaches a of a constant, it will always be a constant. So it's these are called the two important limits, and all of these limit laws can be applied because we actually have two limits. And if you think about this, then when you have two limits, so if I want to find limit x plus 5, I would just say that it is a plus 5, right? And if I want to find limit of 2x minus 2, then it's just as if I'm finding limit x plus 2. So all of these, like snowballing, we can have all these laws. Okay, we have all these laws. Whenever you do limit, you split your function into individual part. You can just use this to work with it. And that indirectly means that, let me go back to the notes. We can, when we want to evaluate a limit of a function, like 3x plus 3 over x squared plus 1, we can just treat these as 3 times of the limit of x approaches a, plug in a to x. So all of a sudden we can have this method called direct substitution. Now we are not to substitute a into x to find limit when we do the concept, but when we evaluate it, it turns out that for some of the cases we can actually do direct substitution to evaluate limit. What is the restriction? The restriction is it is polynomial, rational, root, power of function, and also if you look at the previous rule, click carefully. The important thing is the denominator. If I plug in a, okay, so I plug in a. I don't care what f of a is. This cannot be 0. Okay, if you have this requirement, if this requirement is satisfied, we can actually use direct substitution. We can just plug it in, just like this one. We plug in a to x. I get the limit. So the direct substitution is really because of this limit that we can plug it in. So let's do this evaluate of this limit will be 3 times 0 plus 3. Remember, we're not building the table. We're actually evaluating it. And when we evaluate it, because of the limit law and because of the two limit, we can actually do it that way. And it would be the limit. If you build a table, the table of values of f of x will approaches 3. And this is a root, and this is no divide by 0, so I just plug in. Okay, 6 times 2 plus 4, so equal to square root of 16, equal to 4. And this is also no divide by 0, and it's just algebraic operation of x. It's like polynomial and stuff. So I would just do 5 minus 4 to the cube. The limit is 1. That means if I get a table of values or if I graph them, the 2 points with approaches for values that's close to 5, f of x will be close to 1. Okay, so just again, a warning. Direct substitution will only if the denominator is not 0. So what happens if the denominator is 0? Because we are very concerned about this is because when we do second line, the change of y over change of x, the denominator is actually very close to 0, right? So this is really our major concern. So if we have 2 cases. One is f of a, right, over g of a. The first case is if we have plug in and it's 0 over 0. We call it indeterminate form. So this one, indeterminate form. When we have 0 over 0, it usually points to the fact that x minus a is a factor for both of them. So we could replace this. We could replace this function by canceling the factor. So factor and cancel with another function that is defined at x equal to a. That means we will not have a denominator that is equal to 0. So if we have 0 over 0, we'll use algebraic method to see if we can cancel and factor. Remember, it is because x minus x, this particular factor points to the fact that there is a common factor. We cancel it, and it will become another function, x approaches 1, x minus 4. Now, this function is different from the original function. In this function, x minus 1 is defined. It's like solid. But the first function here, in at x equal to 1, there's a hole. But in terms of limit, they are the same. So it doesn't matter that we can replace it, because we replace it so that we can find the limit. The limit itself is the same. The function is not the same. Okay, we're not talking about replacing with another function. It's just another function where just one point is different. So now there's no divide by 0. I can replace it. 1 minus 4 equal to negative 3. So the second one is x squared minus 4, x minus 2. So if I substitute direct substitution, is 0 over 0. Always check that first. 0 over 0 is indeterminate, so I have to do factoring, cancel. X minus 2 if I factor the top, and x plus 2 if I factor. And then the bottom is x minus 2, so I can cancel it. Now I have x plus 2. So is equal to limit, the same limit, x approaches 2, x plus 2. If I plug it in, is not 0, so that's equal to 4. So this is the same limit as for this, as well as the new one. But they're the same. They have the same limit. Like one is a solid dot, one is an open dot, but limit-wise, they're the same. The third, oh, this is really small. Let me make it a little bigger. It's really small. The third is 6 squared minus 2x minus 3. So let's put, and then we say x approaches negative 1. If I plug in negative 1, I have 1 plus 2 minus 3. I plug in negative 1 is negative 1 plus 1. Oh, it's 0 over 0. That meaning this is indeterminate. I do not know what the limit is because they're both approaching 0. It's like a hole in the function. So I need to factor x minus 3, x plus 1, right? X minus 3, x plus 1. Because I'm going to factor it as negative 3 and negative 2. Two numbers, when they multiply, they are negative 3. But when they add, they're negative 2. So and then I do x plus 1. X plus 1 cancel. So the limit is the same as doing the limit for a new function. X approaches negative 1, x minus 3. Putting negative 1 to minus 4 is to negative 3 is minus 4. So this is the limit. So it's the same here. So you just keep on factoring. Maybe we'll do it in class. So that's the first method. The second method is if you don't if you see radicals, you would find the limit, replace the limit by multiplying conjugate. So we know conjugate means if I have x minus a, the conjugate is square root x plus a, right? If it is square root x plus a, then it's square root x minus a. So but this has to work if I have a 0 over 0 first. So let's check. Square root 4 minus 2 over 4 square minus 16. Of course, it is 0 over 0. So 0 over 0, we have to check, find another function by conjugate. The conjugate of square root x minus 2 is square root x plus 2. We do top and bottom. And the bottom is still x squared minus 4x. Okay. And then we do square root x plus 2. The top, so now the bottom don't multiply. The top will become x minus 4. A squared minus b squared. A squared minus b squared. And then the bottom would be x squared minus 4x. It will be a long function like that. But if we factor the bottom a little bit more, you will see that x minus 4 is actually one of the factors. So instead of multiplying, we actually factor it. X minus 4 canceling, we would have 1 over x square root of x plus 2. Oh, this is actually should be a x plus 2 like that, just a square root x plus 2. Like that. Now this function, when we plug in x equal to 4, would not be 0. We would not have a denominator of 0. So now we do the direct substitution. 1 over 4 square root 4 plus 2 is 1 over 16. So when x approaches 4, this function's limit is 1 over 16. So we'll do this in class. This one is a little more complex. Do this in class. So when you see a conjugate, when you have a conjugate, you will do divide by 0. So when you have a complex fraction and you have also 0 over 0, let's try substitution first, right? It will be 4 minus 1 over 4 over 0, right? When we plug in, and of course that 0 over 0 is indeterminate. So we will do complex fraction simplification, meaning we'll add the fraction together. X plus 4, 1 times 4 times 4, minus 1 x plus 4 over 4 x plus 4. This common denominator over x. This actually is used a lot in the real limit. So we would have 4 minus x plus 4 over 4 x plus 4 over x. And if you do distribute, it would be negative x over 4 x plus 4 over x. And that would equal to, that means times x, right? So this would become times 1 over x. And x cancel. So that's equal to negative 1 over 4 x plus 4. Now, if I have x approaches 0, this will not have a 0 denominator. So we'll have negative 1 over 4 times 4 equal to negative 1 over 16. So these are the method that we use when we want to calculate limit analytically for rational polynomial function or complex function that are rational polynomial type. If they are not 0 over 0, we use substitution. If they are over 0 over 0, we use either factor and cancel, multiply conjugate, or simplify complex fraction. And that would give us a limit, exact value of a limit. So what happens if limit law does not apply and is not 0 over 0? We will have another method. So that will be covering 2.2 part 2.